Welcome everybody to the introductory lecture on model engineering. On today's agenda is that we kind of introduce the basic notion of abstraction, which is an essential notion and concept in model engineering, followed by motivating why we engage in modeling after all. So let's start talking about abstraction. The human mind continuously reworks reality by applying cognitive processes. And one of these cognitive processes is abstraction, where we try to reduce the complexity of the aspects that we are observing for means of proper understanding. And abstraction can then be further classified in three different means. One is generalization, so we generalize specific features of real objects. The other is classification, where we classify the objects into coherent clusters. And the third one is aggregation, where we aggregate objects into more complex ones. And a model and a conceptual model is kind of applying those three means of abstraction. And we can find the first kind of definition of what is a model by means of saying a model is a simplified or partial representation of reality defined in order to accomplish a task or to reach an agreement. And what does it exactly mean, we will learn throughout this course. So a model always represents a certain system under study. The system can be a computer system, it can be an enterprise, it can be a university, whatever it is. Yeah? And the model always is a representation of that system. So it's by definition not the actual system, but it's only a representation thereof. And the model always has kind of three qualities that make this a model. The first quality is a mapping feature. So a model is based on an original, i.e. the system that it represents. A model always has a reduction feature. So a model only reflects the relevant selection or the relevant parts of the system that we are observing, thereby reducing also the complexity. Once the model would represent all of the aspects of the system, it would be identical to the real system, and then it would lose its quality of reducing the complexity, right? And the last quality is pragmatic. So each model follows or has an intention to serve and to support a well-defined, a predefined purpose. Yeah? So a model only serves a purpose. It's not a means to an end by itself. And this purpose can be classified into prescriptive, meaning we create a model to actually build a system in the future. So the system that it's not given yet. The other alternative is descriptive. So we have an existing system, like an existing software system or an existing university, and we try to create a model that represents part of that existing system in a descriptive way. Theoretically, also there are prescriptive models. This is what we also observe in the machine learning models, where we have models that can also predict future states of a system. So why do we engage in modeling after all, and what is model engineering? Model engineering perceives the model as a central artifact of software engineering, and in this respect a model can serve a quite diverse set of different purposes. It can support static analysis, rapid prototyping, automated testing, code generation, or it can also serve some basic but very important purposes like documentation. Yeah? A model as a means of a communication between software designers, like software architects, and software engineers responsible for implementing it, or an agreement between the software engineers and the software testers, for example. Yeah? So a model can follow or can support different purposes. And in model engineering as a generic discipline, we acknowledge these different roles that models can play and emphasize at the central role that the model plays to enable all of those features. Related terms that you will find in the literature and also in the media is model-driven engineering, model-driven software development, model-driven architecture, and we will talk about all of them in the next lecture in some greater detail and kind of try to unbox similarities and also the different aspects of these different terms. So why do we need model engineering after all? Why can't we just build software right from scratch like we did in the past? Yeah? And the basic explanation for that is that we say software is getting more and more complex, and likewise also the technology that we use to build software is getting more and more complex. So 20 years ago, you would build software with one programming language. Nowadays, each software is composed of a set of different heterogeneous programming languages, programming frameworks that you plug in. If you think about the microservice architectures, you can even have microservices with their own data, with their own programming language deployed on their own environment and infrastructure, all together kind of realizing a complex software system. So we inherently have an increasing complexity in the technology stack and also in the software that we try to build. And every time that we talk about complexity or complex systems, we need to reduce this complexity as human beings in order to cope with it. And as I mentioned earlier, modeling is the tool that we apply to reduce the complexity of a certain domain for a specific purpose. Yeah? And in model engineering, we use the model for the purposes of testing, documenting, or generating parts of the code of this software. Yeah? And this is why we say model engineering is at the heart, and it's getting more and more importance with the increasing complexity of our software systems. So the traditional use of models in software development then is, of course, like I mentioned, communication, which might sound very uninteresting, but it's a very important means if you work in heterogeneous groups, in larger groups of software developers. It's very important that you have a common means of communication. And models help to communicate by providing a common and a well-defined language you use to communicate. So we don't use natural language, which is fuzzy, which has very weaknesses, which can be differently interpreted by different people. Instead, we use a well-defined modeling language. We create models as a means to communicate our message, right? And if the sender and the receiver of this model know the modeling language that was used, they can interpret the model in the same way. That is the basic idea, right? Of course, they can also support the software design by capturing the intention of the software system. They can be a means to specify the task for the programmers, or even also to visualize code. So if we think about the reverse way, where we have a software system and we apply reverse engineering to generate a model that represents the existing software, we can also try to cope with the complexity of a running system by having an abstract view on this system by means of a model that represents, for example, the architecture of the different classes and how they work with one another to actually realize the software system, right? And by applying this abstraction, we can, in a stepwise manner, understand the complex system. That is the basic assumption. And what is now the difference between model-driven engineering and model engineering? So in model engineering, we perceive models as the central artifact that can play these different roles, but they don't necessarily need to play all of them. For example, code generation. Yeah? Whereas in model-driven engineering, the driven means that the model per se drives the entire engineering process, right? So every kind of stage of the engineering process is driven by editing a model, creating a model, generating code out of a model. Yeah? So the model is really the central artifact that drives the entire engineering process. What is also important is you should never mistake the model for the reality. I already mentioned that a model is a simplified representation of the relevant aspects of the reality for a specific purpose. And one model that I always like to relate to explain this is the map of the public transport system. Here's the map of Vienna, for example, the public transport system. And you can see all of the qualities that a model has. We generalize, for example, the direction of the underground lines. We don't have the real curves that the underground lines take to go from A to B, but we generalize the direction, because for this map it's not meaningful to know exactly the routing and the curves, but it's very important to know the direction in which the underground lines are running. At the same time, we generalize to some extent the gaps between the different hops, They are normalized and generalized to some extent. There are differences between long and short stops, but this is not one-to-one reflecting the actual distances between the stops, because this is also not essentially a feature, a purpose that this model shall support. At the same time, we classify. We classify all the stops that belong to the U2 line with the purple color. We classify all of them that belong to the U1 with the red color. So thereby we color code and classify similar things that belong to the same class of things, right? And thereby this model is a simplified representation of Vienna, because it abstracts away all of the streets, all of the buildings, all of the districts that we have in Vienna, because the essential and sole purpose of this model is communication of the public transport system by means of saying, how can I go from A to B? Where do I need to enter? Where do I need to switch lines? And in order to arrive at my destination. And this is very intuitive. Tourists also coming from abroad, they look at this map and you get immediately an impression, how can I go from A to B without, looking at complicated information and complicated information systems. Yeah? So this is very intuitive. But again, it's not the reality. It's a simplified representation for the specific purpose. So don't mistake the both of them. Let's look at the three different roles that conceptual models can play. We said prescriptive and descriptive. So prescriptive here is an example, computer-aided design. We have a model representation on the lower left area where we design kind of the architecture on a computer chip, and this is then used to actually produce the chip on the right hand, on the lower right side, to actually produce it. So we can position transistors, we can define the routes of the how the energy is flowing, and all of that matters. We can define them in a model-driven way, and then at CAD program will interpret this model and will then produce the platines, for example. In a descriptive way, one example is the heliocentric model by Copernicus. Copernicus said actually Helios, so the sun is the center of the universe and not the Earth, which was kind of a preceding understanding before that. And then he uses, this could also be perceived as a model where we generalize again, we generalize the distances, we classify the different planets and the different orbits in our enterprise. In our universe, we use the same color coding. We use blue circles to identify the different planets. We use the green lines to kind of represent different distances, right? And you see already, this is not at all adequate one-to-one, reflecting the real distances or the real data that we have, but it serves the purpose of communication, of getting an intuitive, easy understanding how our universe is organized and what is the relationship between the planets. So the application areas of modeling in software engineering can then be generally classified in three ways. Models as drafts, also taking the time perspective. We started off several decades ago using models as drafts. So the objective was communication of ideas and alternatives by the creation of models. And then different software engineers can communicate, can discuss, and can agree on the best design before actually starting with the development of the system, of the software, right? This then kind of emerged toward models as guidelines. So design decisions are documented and the model kind of represent an agreed artifact and provide instructions for the implementation. And then eventually we are now in the phase where we say we can even use models as programs. So models as source code, or models that source code can be generated from. And this is of course the highest possible way and the most beneficial way of using models in the software engineering domain. And this is also reflected, or kind of this means of abstraction, if you look at the history of how programming languages and in software engineering, software development generally evolved. So we started off with a assembler code which was very, very close to the machine executing something. And now with every 5 to 10 years we apply higher abstraction layers. We start to abstract from the assembler toward procedural calls. Then we even developed some libraries. Then we developed some components to what we are talking about the business objects in the domain that the software is actually representing. Yeah. And nowadays you could even also add an initial layer where you say we have kind of computational libraries that we can flexibly plug in and plug out and use and customize only for our purposes. Yeah? So software engineering is continuously trying to develop higher abstraction levels for the same purpose as why we create models, to make it easier for people to define in a more natural way what they actually want to achieve, instead of using assembler and really specifically saying which directory to read, which directory to write, which is much more cumbersome, of course, and it won't scale with the complexities of our today's software ecosystems. If we look at the software ecosystems nowadays, we also need to kind of account that models play a role in the entire life cycle of a software system. So it's not only the analysis, also the design, the simulation and the testing, and also then the operations. So models can also play an important role in the operations. At the same time, we are much more going into agile software development, of course. So the software is not, fixed for several months or years, but we are continuously updating the software with new features. We are continuously debugging and testing the software, or the infrastructure on which the software is running is continuously evolving and we need to adopt. So all of this, of course, increases the complexity of developing and running software systems. And again, this is the incentive of why we say models can play an important role in software engineering. And there's also some very nice examples of how this can also support, for example, the transition of a monolithic, huge software architecture toward a more fine-grained microservice architecture. So for example, this is one paper that has been proposed already in 2011 in the IEEE Transactions on Software Engineering, which is one of the most prestigious journals for software engineering research. And what they have done, they created a model that represents kind of the different classes and the different methods that are adhere to a monolithic software system, and then try to find a modular structure by using genetic algorithms and a multi-objective search. Yeah? So they represented the existing monolith in a modeled way, and then this model was used as an input to the genetic algorithm. It was attached with some objectives like have a high cohesion, a low coupling between the different modules, and then the genetic algorithm would try to shuffle and to assign the different components to different modules in order to find a nice modular, maybe a microservice-like architecture that is much more scalable, much more flexible, and much more reusable. So we see a motion there, computers everywhere towards software everywhere that we already have. And from our research perspective, we think actually the next step is models everywhere. So we can use models in many different ways. And only if you look at the recent discussions in the last year, there's a huge movement toward low code. Yeah, that's a kind of a marketing term. And actually from our perspective, low code is nothing different than model-driven engineering. You use a graphical means to specify software, and then this is interpreted and executed in the background. And all of this complexity of interpretation and execution is kind of hidden to the user. The user works on a graphical visual model interface to specify what he wants, instead of specifying exactly how this is achieved and executed. If we talk about complex systems and their engineering, and this is also very important, we should get rid of the thinking that there is one model or one artifact that we need to produce, like just one Java file or one source code file or a set of source code files in one programming language. Instead, we have many different engineering artifacts that are created throughout the life cycle. Different people are collaborating in this engineering process in order to achieve the final goal. And there are different artifacts on different levels of formality, Word documents, PowerPoint presentations, but also models or or blueprints from electronical aspects, how energy is flowing in the system, what is the functionality of the system, function calls, all of that kind of stuff belongs to an engineering project. And what is another value of models, and we will talk about this later in the course in more detail, is to conceive model as a multi-view concept. So you can have multiple views on one central model, and all of them kind of jointly represent the system under study coherently and comprehensively. So you can have a 3D representation of parts of the model. At the same time, you can have an electrical engineering viewpoint on that model. You can have a state chart model representation like you see on the lower area, or even a functional building block model on the right-hand side that explains the functional aspects of this system. Yeah? And all of those kind of represent the same system under study from different perspectives or viewpoints, using different modeling languages and supporting different purposes, right? So if you look at all of the four little figures that are surrounding the system under study in the center, from each of those models, you can respond to a different kind of question. Yeah? In the 3D model, you can, for example, simulate, and you can ask, respond to questions like, what needs to be the surrounding area that should be restricted for humans to enter, because what is the length of this arm, of this robotic arm in full extension mode, for example. You can simulate all of that, or you can simulate the energy consumption. Yeah? On the lower area, you can ask, what is the functionality that is offered at a certain state of this automata, of this robot? Yeah? And that's just two examples of many to just emphasize every model has a purpose, but also for one system under study, particularly in engineering, we have multiple models, and looking at the underlying modeling languages and their meta-models, a term that we will discuss in detail in the next lecture, we can combine them in order to realize a coherent whole. So that was kind of the introduction to motivate and to introduce the basic notion of modeling. Modeling is all about abstraction. So I hope you understood today the basic means of abstraction, why abstraction is continuously gaining more and more importance, and what role abstraction plays in modeling. And also I hope you understood that the different motivations and the different roles that models can play in software and systems engineering. Thank you very much, and next time we will talk about meta-modeling. Thank you.